source for multimode propagation. For multimode propagation, we use LED structures. Efficiency, LED power, and modulation of LED. Then another light source material which is being used in optical fibers is laser diodes. Light simulated emissions of radiation. So this laser is used single mode fibers. So the mode theory behind that, rate equations and quantum efficiency determination we are going to see in this presentation. Frequencies for laser diode structures and the radiation patterns. Then a specific application called a single mode laser, its modulation, the temperature effects, and extension to quantum lasers, and finally fiber amplifiers is your presentation on optical sources. So before starting the session, I would like to get any feedback from any of you or any queries till unit 1. And if there are any queries of unit 1, you can type in chat box. Some 5 minutes time I'll give you. Then I'll start the unit 3. Okay. Mukesh Sai, giving your valuable feedback. Okay, I think move on to the direct and indirect band gap materials. So you can see the diagram which is drawn energy versus momentum. You see the upper is a wave structure which is a conduction band, at the bottom band, and the gap between the area between the valence band and the band gap. Okay, you can see in two different diagrams. So make a note of this diagram. I'll explain you what it is. The band gap, the minimum energy difference between the top of the valence band, conduction band. The top of the valence band and the conduction band are not generally at the same value of electron moment. You can see in the diagram, the first diagram, you can see between the valence band and the conduction band is not this, you see in the second diagram. So at this instance, the band gap is very, here the band gap is very much larger. This you need to make a note. Okay. So in direct band gap, the top of the valence band will occur at the same value of momentum. The indirect band gap, the maximum energy of occurs at a different value of momentum to the minimum energy. So this we call it as indirect band and direct bands. Diagram you can say which is direct band and which is indirect band. Diagram illustrates the direct band gap semiconductor material. So this is your second diagram, indirect band gap semiconductor material. In a direct band gap semiconductor material, the top of the valence band and the bottom of the conduction band value of momentum. You can see. So here the momentum is going at this, the top of the valence band and the bottom of the conduction band will occur at the same time. So whereas it will occur in direct band gap. So this is how we classify materials. Okay, what is band gap? Band gap represents the difference between the valence band and so now let us the basic optical source that we are going to use is your LED. Okay, this valence band and the conduction band and band gap, learn when we draw the characteristics of LED and characteristics of, so there it will be useful. So for the time being you need to know what is a direct band gap and what is indirect band gap. If you know that, that's more than enough for the time being. Okay, LED, light emitting diodes, and semiconductor device which has the property of propagating incoherent light. Incoherent light. Okay. Through spontaneous emission. Keep in remembrance, this light emitting diode is always spontaneous emission. So what is, whenever you trigger or whenever you give a supply or whenever you give a, or whenever you pass a current through the LED, it will glow, it will emit light. So this is what spontaneous emission is. Laser is a stimulated emissions. LED is a semiconductor device that emits incoherent light emissions whenever a current is passed through it. So typically these are used for optical communication, are being fabricated depending upon the first window, third window. Why? Because in first window we are using a different wavelength, second window different wavelength, third window different wavelength. So depending upon the wavelengths, the combination of the LED structures also vary. So the first window, which is operating at 850 nanometer, the LEDs were fabricated using gallium arsenide and aluminum gallium. So this is discussed in unit number 1 before itself. Then for the second window, which is at around 1300 nanometer, and the third window 1050 nanometer, the LEDs are being fabricated gallium arsenide phosphide and indium phosphide. Three different windows or the three different wavelength regions on which the optical waveguide is being used, and the corresponding LED materials. What are the different materials used in different window systems of optical fiber? So there are different types of LEDs that are used in optical communications. Some of the basic is your surface emitting LED. LED, we call it as SLED and so SLED represents surface emitting light emitting. ELED represents edge emitting light emitting diode, and there is another which is used nowadays is your superluminescent diodes. Luminescent diodes. So depending upon the performances, depending upon the links, the being changed or devices are being utilized, the need and necessary. For shorter distances of about 0 to 3, we can go for a low data rate fiber optics, where surface emitting LEDs and edge emitting LEDs are the preferred optical sources. So if you want to go for higher distances, 100 kilometer and all, the superluminescent diodes are being utilized. These surface emitting LED with a bit rate of up to second, 25, 250, not 25, 250 megabits per second. Since these surface emitting LEDs emits light over a wider area, they are almost exclusive in multi-mode systems, LEDs. For medium distances that have medium data, edge emitting LEDs are preferred. So the edge emitting LEDs with a data rate of up to 400 megabits, surface 250 megabits per second, edge 400 megabits per second. So these edge emitting LEDs are used for both single mode and multi-mode fibers for longer wave distances, long with high data rates. Next is the superluminescent diodes. So these are based on edge emitting LEDs designed to operate in superluminance mode. So in superluminance mode, the optical fiber or the optical fiber cable will transmit it more than 400 megabits per second. Also, the introduction of LED configuration towards the types. So next we'll see a specific type of LED, which is surface emitting LEDs. This is your diagram emitting LED. In this surface emitting LED, we have a sink. You can see at the bottom heat sink. We have then we have P-type gallium arsenide. This layer is made up of P-type gallium arsenide. It is made up of P-type aluminum gallium arsenide. Then next layer is made up of N-type or P-type gallium arsenide and N-type aluminum gallium arsenide. In this surface emitting along the surface P-type gallium arsenide, we dig a edge or well such that on spontaneous emission will occur in the double heterojunction layers. This is your double heterojunction layer. Okay. Layer. So as you had studied in VLSI design, fabrication of an IC is the same process using a double heterojunction layer. So NP or NPP. This is your circular contact region, this part, and active region. So when current flows, electrons from this region will move on and it will emit light. So that light is being captured through the where an optical fiber is being impulsed. So you can see well is being etched such that you can connect it to the optical. Okay, then we have the metallizations, and then optical fiber is being inserted. Surface emitting, whereas you can see this is a surface. I'll show you and explain you edge afterwards. So let us see the surface. So this surface emitting LED is also known as the Bourus because it was developed by C.A. Bourus on his name. Oh, sorry. Hence the name Bourus LED. So this emitting LEDs, the primary active region is limited to a small circular area of about 20 micrometer to 50 micrometer. Rewrite it. The active region LED where photons the primary active region is shown in the diagram, which is below the surface substrate perpendicular to the axis of the fiber. A well is etched into the substrate, coupling of the emitter light to the optical fiber. So this allow the optical fiber to come in close contact the surface emitting LED And in addition, that consists an epoxy resin that is being applied onto the LED such that optical fiber sticks to the surface light emitting diode to reduce index mismatch, thereby increasing the coupling efficiency. Diagram of surface emitting LED. You can have a view. You can see the primary region is along the surface. Since I couldn't find any queries in chat box, I proceed on to the next slide, which is edge emitting LED. First, I'll show you the diagram of the edge emitting. Here also we have the same double heterojunction layer. We started from the sink. The next layer is metallization, then substrate made up of indium phosphide, then another N-type indium phosphide. Above that, indium gallium arsenide phosphide of P-type or N-type placed. Then on the above, N-type indium phosphide, then P-type indium, then the silicon dioxide or the substrate, then metallization, then the strip contact. And here is the optical beam. So point just towards this edge is your edge emitting light emitting diode. This is the diagram. So the surface emitting is used for edge emitting for medium data rate. Here also we have the same double heterojunction layer. The material composition is different. You can see this arsenide is being used. In edge, indium phosphide is being used. So the difference is surface emitting along the surface of the LED, the optical wave will be as here at the edges of the. So the demand for optical sources for longer distance and with systems operating at longer led to the development of LED. This shows the different layers of semiconductor in edge emitting LEDs. The primary active region of the edge emitting LED is narrow stripe, which lies below the semiconductor substrate. So the semiconductor substrate is cut or polished, runs between the front and back of the device. So the polished or cut surfaces at each end of the stripe are called facets. You can see this is the facet. In a in an edge where facet is highly reflective, in the front face is anti-reflection curve. The rear face, which is the rear facet, reflects the light propagating towards the rear end face towards the front facet. By coating the front facet with anti-reflection, reduces optical feedback and allows light emission. The edge emitting LEDs emit light only through the facet. Since the rear facet is being coated with anti-reflection coating. The edge emitting LEDs emit light in a narrow emission, allowing for a better source to fiber coupling. These couple more power into the small numerical aperture fibers, the surface emitting LEDs. The edge emitting couple enough power into the single mode fibers for some specific applications. LEDs emit power over a narrower spectral range than the surface emitting. Stages of edge emitting over surface emitting. This edge emitting LEDs are more sensitive to temperature fluctuation. Variations of temperature will affect the edge emitting as compared to surface emitting, which is a greater disadvantage. In order to show the difference between the structure of edge emitting and surface emitting, I'm going to put this to this slide and I'm going to show you. Such that you can easily differentiate what is surface and what. In terms of the left hand side is your surface emitting, your edge emitting. You can see the surface emitting LED structure and right hand side light emitting diode structure. You can see both. So any doubts in this types of LEDs? Any queries you can type in chat box. Some 5 minutes of time is being given. Any queries, type in chat box. Try to visualize different types of LEDs such that you can able to surface which is edge. Okay, since no queries in the chat box, I'll proceed on to the slide, which is the rate equations and quantum efficiency of LEDs. So when there is no external carrier inject, the excess density decays the electron hole recombination, which can be given as n into e power t divided by t naught. Excess carrier density, n naught is the initial injected excess cell, tau is the carrier lifetime. So here we can find the bulk recombination rate equal to minus dn by dt or n by t. Bulk recombination rate equal to the radiative recombination rate plus the non-radiative recombination rate. So the bulk recombination rate is 1 by tau, whereas the radiative recombination rate is 1 by r, and the non-radiative is 1 by tau nr. Of these two, we get bulk recombination rate. And externally supplied with current density J, then the rate equation for the electron hole recombination will become dn of t divided by dt is equal to J divided by qd minus q is the charge of the free electron, d is the thickness of the recombination region. So n is jt divided by qd during equilibrium condition. Next is the internal quantum efficiency, which can be obtained by eta int, which is the in the active region, how much amount of power generated is given as RR divided by RNR. This tau NR divided by tau NR. The optically generated power inside the active region of the LED is of surface and edge. It is power internal, which is P int internal optical power is equal to eta int internal quantum efficiency into I divided by Q. Okay. I is the injected current into the active region. Next, we need to find the external quantum efficiency, which is defined as number of photons emitted from LED to the ratio of the number of LED internally photons generated. So in order to calculate the external efficiency, we need reflection effects at the surface of the LED. So this efficiency is obtained the ratio of the number of photons emitted divided by photons which is generated internally. So this is how LED power can be calculated. So this is common for both emitting. We have the LED facet, we have the confinement layers, the guiding. So here the light occurs and they are being guided towards the facet. So here the light is emitted waves. So emitted optical power can be obtained by power is equal to power P external efficiency into power which is being generated, which is approximately equal to power internally generated divided by into n1 plus 1 the whole square. N1 is the refractive index of the core. N2 is the refractive index of, which is obtained by the Fresnel equation P naught of 0. So which is 4 N1 N2 divided by N1 plus N2. So if N2 is 1, so then Fresnel quantum efficiency will be divided by N1 into N1 plus 1 the whole square. So which is obtained as the optical LED power. Next is the modulation of an LED. LED depends upon the doping level, the injected carrier lifetime in the recombination region, capacitance of an LED. So if LED is modulated at the frequency of omega, then the optical power of the device will vary as such. Power of the P naught divided by square root of 1 plus omega tau I the whole square. So next is the electrical current density. Electrical current density is proportional to the optical power. So hence you can define the electrical bandwidth and optical bandwidth separately. So 10 log of the base 10 P of omega divided by P naught, it is 20 log I of P naught. So P represents your electrical power and I represents your electrical current. So when a graph is drawn with respect to frequency and the current in terms of electrical 3 dB point and optical, you need to make a note like this. So if one is drawn, the electrical bandwidth is always electrical 3 dB point, which is obtained at 7. And the optical 3 dB point or the optical 0.5 of current ratio for optical 3 dB. So this is optical band. So the optical bandwidth can be obtained by 10 log P of omega divided by P of naught, which is equal to omega divided by I of naught. So there is a difference between electrical band, optical bandwidth. So next topic is laser. So this laser is meant for only a single mode of in single. So the laser contains only a single frequency, where we have multiple frequencies because there are multi-modes being used. So this laser is more a simple lens system to an extremely small point. There is no aberration since chromatic dispersion since only one wavelength is, and also all of the energy from the light source is concentrated to a very small spot of light. So the abbreviation for known to you all, which is laser amplification emission of radiation. So let us see the working of this. So we'll construct the laser first, then we'll see the working. So the laser consists of an arsenate which has been doped with elements such as selenium, aluminum, or silicon. Use P-type and N-type semiconductor materials. A laser has an additional active layer of undoped, which is intrinsic. that is gallium arsenide, will have the thickness nanometers. So it is sandwiched between the P layer and the N layer as shown in the figure. I'll show you that, effectively creating a pin diode. It is P-type intrinsic. So it is in this layer that the laser light is produced. So this is your laser. So you have the anode and the cathode. Here is the aluminum gallium arsenide N-type layer and the aluminum gallium arsenide. Between these two, an undoped active region is being sandwiched such that it emits light. So this is where it is being emitted. So these surfaces are polished, partially reflective surface. These surfaces are mirror polished reflecting surfaces. Here the comes out in single direction. There is a residual light. So this is a can type laser. You can see you have a cap, you have laser chip. This is your pin photodiode. This is this is it. So P layer intrinsic, undoped active region, and the N type. So pin type layer is being used. So how does this works? So the laser works in the following principle. So every atom, quantum theory, will have energies only within a certain discrete energy. The atoms would be present in the lowest energy state or in the ground state. So when an energy source is given to the atoms in the ground state, they are excited and they move towards the. So this process is called as absorption. So after some time, electrons will stay at that very short duration. Then the will return to its initial ground state, emitting a photons in the. So this process is called as spontaneous emission. Which is absorption spontaneous emission, takes place in a conventional light by emitting laser light. So procedure we call it as population inversion, which you all are familiar. So here is the at ground state. It is excited. It is moving to the ground level. It is during emission and after emission, it comes down. So excited level and the grounded level. During this, the incident photon h nu is being generated. So E2 minus E1, which is del E, gives you photons. Which is given here. When favorable conditions are created for the stimulated emissions, more and more atoms are forced to emit photons, thereby initiating a chain reaction and releasing an amount of energy. So this results in a of energy of emitting only a single length or a monochromatic light, which travels coherently in a direction. This process is called amplification by stimulated emission. Of atoms in any level at a given time is called the population of that. Normally, when the material is not excited externally, of the lower or the ground state is greater than that of the upper state. When the population of the upper state or the upper level exits that of the lower level, which is the reversal of the normal occupancy process as population inversion. Simulated emission takes place. Next is the double heterostructure, which is the basic structure which I had shown. The double heterojunction laser diode is made up of sandwiching a low bandgap material with a layer of either a side of high bandgap layers. In between that, we have a gap. So this makes sense as the materials themselves are different and not just with different types of doping, p-type and n-type. Metals used are your gallium arsenide, as shown in the diagram. So the advantage double heterojunction laser over the other types is that holes and to the thin middle layer, which acts as the active region, so which is the intrinsic region. By containing the electrons and holes more effectively, there could be possibility of more electron hole pairs available by increasing recombination and amplification. Next is the quantum well laser. The quantum well laser uses a very layer which acts as a quantum well where of the electron wave function is quantized. Quantum well has an abrupt edge. This concentrates electrons that contributes to the laser action and increases the efficiency of the system. So in addition to the single quantum well lasers, multiple also exist. So the presence of multiple quantum overlap between the gain region and the optical waveguide modes. Upon the necessity, single quantum well or multi quantum well can be used. The basic operation of an optical amplifier. After the input signal, either from your LED or laser, is being obtained. So we have the optical signal which is being generated in pulses. Then we have the Doppler which is being present. Medium is by the pump source. Then the couplers. Then the amplified output signal. So this is the basic. Okay, that's all for today's presentation. Any